Hello, I'm going to finish up Lesson 19 by going over all of the material we have covered in Math 65. You may have noticed we covered a whole lot of material, so I'm going to be doing a whole lot of reading in this lesson, and I'm also going to work several very short, very pointed examples. One thing I'm not going to do when I work most of my examples is check my solution. Checking solutions is an important part of the process. After watching this lesson, you should get out your Math Telecourse packet and get out the practice final and work through the problems. In Lesson 20, Candace, Ann, and I are going to work through all of the problems in your practice final, and I guarantee you we will be checking solutions there because, as I just said, checking solutions is an important part of the process. So what all have we covered this term? Well, we began by talking about systems of equations. We also talked about exponents and square roots and polynomials. Lately, we've been talking a lot about quadratic equations, and we finished up by talking a little bit about functions. So let's begin by reviewing systems of equations. A solution to a system of two equations and two variables is an ordered pair that is a solution to both equations in the system. Let's see an example. 3, 2 is a solution to the system x plus y equals 5 and x minus y equals 1 because when we replace x with 3 and y with 2, we have 3 plus 2 equals 5, which is true, and 3 minus 2 equals 1, which is also true. Now, the graph of each of these equations is a line, and so we call this particular type of system a linear system of two equations with two unknowns. Let's look at a graph. Here's a graph of the line x plus y equals 5, and here's a graph of the line x minus y equals 1. Notice that the two lines intersect at the point 3, 2. So one way we talked about solving systems of linear equations with two unknowns is we would graph the two lines and find where, if at all, the two lines intersect. If the two lines intersect in a single point, that point is the solution to the system of equations. But the graphing method is not really an efficient method for all systems. So we talked about some other more symbolic algebraic methods. One method we talked about for finding the solution to a system of two linear equations with two unknowns is the substitution method. We begin by solving either of the equations for one variable in terms of the other. So for example, if I had the system 2x plus 3y equals 19 and negative 6x plus y equals negative 7, I could solve the second equation for y and rewrite it as y equals 6x minus 7. We then substitute the expression for the variable solved for in step 1 into the other equation. And we solve the equation in one variable found in step 2. So let's see what that would look like. Here I have the expression 6x minus 7, which I'm going to substitute for y, but I'm going to make the substitution in the first equation. And that's going to give me 2x plus 3 times the quantity 6x minus 7 equals 19. After I go through the solving process, I see that the x-coordinate of the solution to this system of equations is 2. But remember, it's going to take 2 coordinates to be a complete solution. So what we need to do next is substitute the value found in step 3 into the equation found in step 1. This determines the value of the second variable. So I saw that x equals 2. I knew from the second equation in the original system that the y-coordinate is 6 times the x-coordinate minus 7, so the y-coordinate of our solution is 6 times 2 minus 7, which is 5. We need to check the proposed solution in both equations and state the solution, remembering that the solution to a system in two variables is an ordered pair. So here I've gone ahead and taken my original system, I've replaced x with 2 and y with 5, and it sure is indeed the case that 2 times 2 plus 3 times 5 is 19, and negative 6 times 2 plus 5 is negative 7. So our solution checks, and we state our conclusion. The solution is the ordered pair 2, 5. The other algebraic method that we talked about that involved manipulating symbols was the elimination method. The first thing we do with the elimination method is we write the equations in standard form, ax plus by equals c. Then we multiply one or both equations by a number or numbers so that they have pairs of terms that are additive inverses. And we add the sides of the equations to eliminate one variable and solve for the remaining variable. For example, suppose we had this system right here. The system's already written in standard form. So what we need to do is multiply one or both of the equations by appropriate numbers so that when we add the respective sides of the equation together, one of the variables is eliminated. There's more than one choice we could make. I've chosen to go ahead and multiply both sides of the first equation by 3 and both sides of the second equation by 2 because when I do that, I have coefficients of 6 and negative 6 on the x terms, so when I add the respective sides of the equations together, x is eliminated. I'm left with 20y equals 60, so that tells me the y-coordinate of my solution is 3. Now I need to use substitution to find the value of the other variable. I need to check the proposed solution in both equations, and I need to state the solution, remembering that the solution to a system in two variables is an ordered pair. So where are we? Well, I knew that y equals 3 in my solution, so I'm going to go back to my first equation in my original problem, and I'm going to replace y with 3. And when I do that and solve for x, I end up with x equals negative 5. Then I check. 2 times negative 5 plus 4 times 3, that's negative 10 plus 12, which is 2. Negative 3 times negative 5 plus 4 times 3, that's 15 plus 12, which is 27. My solution checks. The solution is the ordered pair negative 5, 3. We had a whole bunch of language that went along with systems of equations. Independent equations graph two distinct lines. A linear system of two independent equations can have one solution or no solutions. Dependent equations graph to the same line. A linear system of dependent equations has an infinite number of solutions represented by the points on the given line. A consistent system of equations is a system of equations that has at least one solution. And an inconsistent system of equations is a system of equations that has no solution. That was a whole lot of words. Maybe we could get a better grip on this with some pictures. Here we have a system that presumably graphs to these two lines. And we see that the two lines intersect in a single point. So there is a solution to the system. It's this point of intersection. So this is a consistent system with exactly one solution. The equations are independent because they graph to two distinct lines. Well, what's another relationship the two lines could have? They could be parallel, and parallel lines never intersect. Consequently, there is no point that lies on both lines. Consequently, there is no point that satisfies both equations. This is called an inconsistent system, and it has no solutions. However, the equations are still independent because they graph to two distinct lines. There's a third possibility for the orientation of the two lines, and that's that they are in fact two different symbolic representations of the same line. This is a consistent system, but there's an infinite number of solutions. Any point on this common line satisfies both equations in the system. In this circumstance, we say that the equations are dependent. The equations are dependent when they graph to the same line. So suppose that we were trying to solve a system of equations using the substitution method or the elimination method. How would we recognize that we had an inconsistent system or dependent equations? Well, systems of equations that simplify to a false statement are inconsistent. Inconsistent systems have no solutions. False statements are statements that equate two unequal numbers. For example, 0 equals 8. That's just plain false. Systems of equations that simplify to an identity have infinitely many solutions. The equations in the system are dependent. One type of identity equates two equal numbers. For example, 7 equals 7. That's an identity. So let's discuss a couple systems of equations. What if we had x plus y equals 5 and negative x minus y equals 1? Well, if we wanted to eliminate x, we could just add the respective sides of the two equations. But what happens when we do that is we also eliminate y, and we're left with the contradiction 0 equals 6. 0 equals 6 isn't going to happen regardless of what numbers we replace x and y with. So this system of equations is inconsistent. The system has no solutions. How about this system? Well, again, if we aim to eliminate x, we could achieve that by adding the respective sides of the two equations together. But again, when we do that, y is also eliminated. But something different is happening here. This time I'm not getting a contradiction, I'm getting an identity. 0 equals 0. That's always true. It must be the case that these two equations graph to the same line, and every point on that line satisfies the system. These equations are called dependent because they graph to the same line. The solution set is the set of points x, y, where the y-coordinate equals 5 minus x. I got that formula by solving this first equation for y. Let's move on to exponents and square roots. Let's begin with our beginning definition. If b is any algebraic expression and n is any positive integer, then b raised to the m power is the product of n factors of b. b is called the base of the exponential expression, and n is called the exponent of the exponential expression. For example, what's 3 to the 4th? 3 to the 4th is the product of 4 factors of 3. That's 9 times 9, which is 81. We had some other definitions of exponents. X raised to the 0 power is always 1 as long as the base x isn't 0. 0 to the 0 is something we call indeterminate. X raised to the negative m power is equal to 1 over x to the positive m power as long as x doesn't equal 0. So what's the result of raising negative 3 to the 0 power? The result of raising any number other than 0 to the 0 power is 1. Well, what's up with the next example? Well, what I'm trying to illustrate with the next example is that in the next example, since we don't have parentheses around negative 3, we're not raising negative 3 to the 0 power. In order of operations, the exponent is applied before the negation. So all that's being raised to the 0 power is 3. 3 to the 0 power is 1, and we need to take the opposite of that. So the opposite of 3 to the 0 power is negative 1. 4 raised to the negative 2 power is 1 over 4 squared, which is 1/16. Then we had a whole bunch of rules of exponents. We had something called the product rule. b to the m times b to the n equals b to the m plus n. We also had something called the quotient rule. X to the m divided by x to the n equals x to the m minus n. This is assuming, of course, that x is not 0. Let's see some examples. If we had x to the 62nd times x to the 38th, according to our product rule, to simplify, all we need to do is add the exponents, and this is going to leave us with x to the 100th. This rule actually makes a lot of sense. This expression says that I have 62 factors of x. This expression says that I have 38 factors of x. So altogether, I have 62 plus 38 factors of x. How about t to the 16th over t to the 21st? Well, according to our quotient rule, this can be simplified to t to the 16 minus 21 power. That's t to the negative 5 power. But when we simplify exponential expressions, we don't like to have any negative exponents in our final expression, so I'm going to use our definition of a negative exponent to rewrite this as 1 over t to the 5th. So ultimately, t to the 16th over t to the 21st simplified to 1 over t to the 5th. Now I'm noticing that 5 is just 21 minus 16. I wonder if there's a rule that would have allowed me to get to this simplification more quickly. Well, in fact, there is. X to the m over x to the n equals 1 over x to the n minus m as long as x doesn't equal 0. We also have another consequence of our definitions and rules that says that 1 over x to the negative m equals x to the m, again assuming x doesn't equal 0. So let's see some examples. What if I wanted to simplify x to the 7th over x to the 32nd? Well, 32 is a larger number than 7, and when the exponent in the denominator is larger than the exponent in the numerator, you can speed things up if you go ahead and move the factors to the denominator. So according to the rule we just looked at, this is going to be equivalent to 1 over x to the 32 minus 7, which is 1 over x to the 25th. How about t to the 22nd over t to the 5th? Well, you know, if I wrote 22 factors of t in the numerator and 5 factors of t in the denominator, after I was done factoring out t over t from my fraction, I'd be left with 17 factors of t in the numerator. So I think I want to just use the regular old quotient rule to simplify this expression. This is t to the 22 minus 5, which is t to the 17th. How about 1 over 2 to the negative 6? When you're evaluating numbers, you cannot make the actual calculation until all of your exponents are positive. So the first thing I need to do is rewrite this as 2 to the positive 6th power. This is the product of 6 factors of 2, which is 64. Here's another rule. It's the products to power rule. If I take ab to the m power, that's the same as a to the n times b to the n. Verbally, what this is saying is that if I have an exponent applied on a product, I can distribute the exponent to every factor in the product. I also have a powers to power rule that says if b is raised to the m and that quantity is then raised to the n, the final exponent on b is m times n. Let's see some examples. Let's simplify x to the 4th times t to the 7th, all raised to the 11th power. So the first thing I'm going to do is I'm going to use my product rule that says that I can distribute this exponent of 11 to both factors in the product. Now I'm going to use my powers to power rule that says that x to the 4th to the 11th can be simplified by multiplying the exponents of 4 and 11, and t to the 7th to the 11th can be simplified by multiplying the exponents of 7 and 11. Let's think about this powers to power rule for just a moment. The expression x to the 4th to the 11th, if I expanded it, I would have 11 factors of x to the 4th. Each of those factors of x to the 4th has 4 factors of x. So altogether, 11 times I would have 4 factors of x. 11 times 4 factors of x, 44 factors of x. Here's another rule. The fraction a over b raised to the m power equals a to the n over b to the n, as long as b doesn't equal 0. This is called the quotient rule. Also, a over b to the negative n equals b over a to the positive n, as long as neither a nor b is 0. Let's use these two rules to evaluate 2/5 to the negative 3. When you're performing numerical calculations with exponents, you're never going to get anywhere as long as any of the exponents are negative. So the first thing I think I'm going to use is that sort of reciprocal rule that we just saw. We can make this exponent positive if we reciprocate 2/5 to 5/2. Now I can use the quotient rule to distribute the exponent to both the numerator and denominator of the fraction. So this is 5 cubed over 2 cubed, which is 125 over 8. The next thing we talked about after exponents was scientific notation. A number written in scientific notation is in the form a times 10 to the b, where a is a number that's greater than or equal to 1 and less than 10, and b is an integer. Scientific notation is commonly used to express very large numbers and very small numbers. Let's recall that multiplying a number by a power of 10 with a positive integer exponent n moves the decimal point m places to the right. And multiplying a number by a power of 10 with a negative integer exponent negative m moves the decimal point m places to the left. Notice that m is greater than 0. So for example, if we multiplied a number by 10 raised to the negative 3 power, we'd move the decimal point 3 places to the left. We also talked about square roots. The square root of n is the non-negative number that squares to n. So suppose we wanted to know what's the square root of 81. Well, there's two real numbers I can square that result in 81. 9 squared is 81. Negative 9 squared is 81. By definition, the square root of 81 is the non-negative number that I square that results in 81. That would be positive 9. How about the square root of 0? Well, there's only one number I can square that gives me 0. That's 0. How about the square root of negative 4? Well, let's think about this. If I square a positive number, I get a positive result. If I square a negative number, I get a positive result. If I square 0, I get 0. So at least as far as real numbers are concerned, there is no real number that I can square that's going to result in negative 4. So the square root of negative 4 is not a real number. You'll learn in later classes that there's another category of numbers that you can square that do give you negative results. Then we had some square root properties. If a and b are non-negative real numbers, then the square root of a times b equals the square root of a times the square root of b, and similarly, the square root of a times the square root of b equals the square root of a times b. One way we used this was to simplify square roots. When we simplify square roots, one of the things we're talking about is if there's any perfect square factors of the radicand, that's the number underneath the square root symbol, we want to rewrite the radicand as the product of the perfect square and the residual factor and pull out the square root of the perfect square. Now that sounded pretty complicated, so let's apply that to the square root of 150. The first thing I want to ask myself is there a perfect square that evenly divides into 150? Well, the number ends in 50, and that makes me think about the perfect square of 25. And indeed, 25 divides into 150 6 times. So when I simplify the square root of 150, I want to begin by rewriting 150 as 25 times 6. Now, according to the square root rule that we just looked at, this is equivalent to the square root of 25 times the square root of 6, which is 5 times the square root of 6. How about the square root of 2 times the square root of 8? This is actually pretty cool. I'm going to get out my calculator and explore this a little bit. Recall that the square root of a positive integer is always either another positive integer or it's an irrational number. Well, neither 2 nor 8 is a perfect square, so the square root of 2 and the square root of 8 are not positive integers. Consequently, they're each irrational numbers. And remember that in decimal form, irrational numbers, the decimals never terminate, nor do they ever form a forever repeating pattern. Consequently, anything we get off of our calculator for these two numbers is going to be an approximation. The square root of 2 is approximately 1.4142135. And the square root of 8 is approximately 2.8284271. Now suppose I asked you this question. What is the result of multiplying 1.4142135 with 2.8284271? I think your response would be along the lines of, are you nuts? I have no idea what those two numbers multiply to. Well, let's see what those two numbers multiply to. So I'm going to take the square root of 2, and I'm going to multiply by the square root of 8. Holy smokes! They multiply to this nice, neat number, 4. Let's see the math behind that. The square root of 2 times the square root of 8, according to the square root property we're exploring, is equal to the square root of 2 times 8. Aha! That's the square root of 16, which is 4. So in decimal form, this 4 was very unexpected. But using our square root properties, it's very natural that the square root of 2 times the square root of 8 is 4. Here's another square root property. If a and b are non-negative real numbers and b doesn't equal 0, then the square root of a over the square root of b equals the square root of a over b, and the square root of a over b equals the square root of a over the square root of b. So here again, we get something very similar to what we had when we multiplied the square root of 8 and the square root of 2. When we divide the square root of 8 by the square root of 2, the result of dividing these two irrational numbers is equivalent to the square root of 8 over 2. That's the square root of 4, which is 2. One other thing we did when simplifying square roots was we rationalized the denominator. The square root of 5 is an irrational number. The trick we can use to make this denominator rational is we can multiply the denominator by another factor of the square root of 5. Then we'll have square root 5 times square root 5, which is 5, in the denominator. That's rational. But if we just multiply the denominator by the square root of 5, we won't have a number that's equivalent to our original number. So I need to also multiply the numerator by the square root of 5 so that my net multiplication was by 1, and I still have something equivalent to 3 over radical 5. When I perform this multiplication, I'm left with 3 square root of 5 over 5. Let's move on to polynomials. We began with a whole lot of definitions. A polynomial is an expression containing one or more terms added together. The exponents on the variables in each term must be whole numbers. We had a different way for the same definition. A polynomial in X is a finite sum of terms of the form ax to the n, where a is a real number and n is a whole number. Then we had some special names for certain types of polynomials. A monomial is a polynomial with exactly one term. A binomial is a polynomial with exactly 2 terms. A trinomial is a polynomial with exactly 3 terms. A polynomial with more than 3 terms doesn't have a special name. The degree of a term is the sum of the exponents on the variables contained in the term. And the degree of a polynomial is the greatest degree of any term of the polynomial. Then we started doing some operations with polynomials. In a previous algebra class, you learned to combine like terms. Adding and subtracting polynomials is nothing more than this. Then we started multiplying polynomials. And multiplying polynomials sometimes requires multiple applications of the distributive property. Let's see an example. Suppose we want to multiply these two polynomials. 2x plus 3 times x squared minus 5x minus 4. Well, the first thing I'm going to do is I'm going to distribute the trinomial over the 2 terms in the binomial. That's a fancy way of saying that I'm going to rewrite this as 2x times x squared minus 5x minus 4 plus 3 times x squared minus 5x minus 4. Now I need to distribute 2x through the trinomial. This is a second application of the distributive property. That's going to give me 2x cubed minus 10x squared minus 8x. I also need to distribute 3 through the trinomial, so that's a third application of the distributive property. So that's plus 3x squared minus 15x minus 12. Now all I need to do is combine my like terms. I only have one cubic term, 2x cubed. I have 2 squared terms, negative 10x squared and plus 3x squared. That simplifies to negative 7x squared. I have 2 linear terms, negative 8x minus 15x. That simplifies to minus 23x. And then I have my constant term, which is negative 12. So I end my polynomial with minus 12. We had a shortcut for one special polynomial multiplication. That's the multiplication of 2 binomials. And the shortcut is abbreviated FOIL. We take the product of the first terms, we add the product of the outside terms, we add the product of the inside terms, and we finish up by adding the product of the last terms. Let's see an example. Suppose I'm trying to find this product. 3x squared minus 5 times 7x squared plus 10. When we FOIL, we tend to FOIL in our head, but since I'm illustrating this, I'm going to go ahead and write FOIL on the screen. The product of the first terms, 3x squared times 7x squared, that's 21x to the 4th. The product of the outside terms, 3x squared times 10, that's plus 30x squared. The product of the inside terms, negative 5 times 7x squared, that's minus 35x squared. And the product of the last terms, negative 5 times 10, we finish up with minus 50. And I do need to combine my like terms. I have 21x to the fourth. 30x squared minus 35x squared is minus 5x squared minus 50. Then we had a whole bunch of special products. The first two special products are called the square of a binomial. And the final product is called the product of conjugates. Let's see some examples. Suppose we want to find 4x squared minus 3. Well, in the pattern on the last screen, our a value is going to be 4x squared, and our b value, that's what's being subtracted, is 3. So according to our pattern, 4x squared minus 3 quantity squared is a squared, so that's 4x squared squared minus 2 times a times b plus b squared. So simplifying, I have 16x to the fourth minus 24x squared plus 9. In this next example, this is a product of conjugates. Our a here is 3x, and our b is 8. And when we multiply conjugates, we get a, so that's 3x squared, minus b, so that's 8 squared. So this simplifies to 9x squared minus 64. Then we moved on and started talking about factoring. The first step when factoring a polynomial is to identify and factor out the greatest common factor of all of the terms of the polynomials. So for example, suppose I had 48x to the 6th, y to the 7th, plus 16x to the 4th, y to the 8th. Well, when I'm identifying the greatest common factor, I have to consider the coefficient, the x, and the y separately. The coefficient, what is the greatest common factor of 48 and 16? Well, 16 evenly divides into 48 and obviously evenly divides into 16, so I can factor out 16. Both terms have x's. As a matter of fact, both terms have at least 4 factors of x. Both terms have y's. Again, as a matter of fact, both terms have at least 7 factors of y. So this is my greatest common factor. Now, what do I need to multiply 16x to the 4th, y to the 7th to get back 48x to the 6th, y to the 7th? Well, to get the 48, I need to add a factor of 3. To get 6 factors of x, I need 2 additional factors of x, and I already have all 7 factors of y. Plus, what do I need to multiply 16x to the 4th, y to the 7th by to get back 16x to the 4th, y to the 8th? Where I already have my factors of 16 and x to the 4th, all I'm missing is 1 factor of y, so I need to multiply by y. And remember, factoring is something that you definitely want to check. The trinomial ax squared plus bx plus c factors over the integers if and only if there are integer factors of the product a times c that add to b. Let's see some examples. Let's factor x squared plus 5x plus 6. A is the coefficient on x squared, which is 1. C is the constant, which is 6. So a times c is 6. Are there integer factors of 6 that add to 5? Well, of course there are, 2 and 3. So x squared plus 5x plus 6 factors into x plus 2 times x plus 3. How about x squared plus 7x plus 5? Again, a, the coefficient on x squared, is 1, and c, the constant this time, is 5. 1 times 5 is 5. Are there integer factors of 5 that add to 7? I don't think so. What are the integer factors of 5? Well, there's only 2 possibilities, 1 and 5, or -1 and -5. And one thing's for sure, neither of those pairs add to 7. So we say that the trinomial x squared plus 7x plus 5 is prime. It cannot be further factored. How about 4x squared plus x minus 14? Well, this time, a, the coefficient on the squared term, is 4, and c, the constant term, is negative 14. 4 times negative 14 is negative 56. So what I'm looking for is two integer factors of negative 56 that add to 1. So when I see 56, I start thinking about 8 and 7. And sure enough, the difference of 8 and 7 is 1. So the integer factors I'm looking for are positive 8 and negative 7, because those add to 1. Now what I'm going to do with those integer factors is I'm going to use them in a strategy we call factoring by grouping. I'm going to take the linear term 1x, and I'm going to rewrite it as 8x minus 7x. Now I'm going to factor by grouping. I'm going to group together the first two terms, and the first two terms have a greatest common factor of 4x. And when I factor that out, I leave behind x plus 2. So what I want to do now is I want to factor something from the final two terms that's also going to leave behind x plus 2. And what I would need to factor is negative 7. So I have 4x times x plus 2 minus 7 times x plus 2. These two terms have a common factor of x plus 2. And when I factor out the common factor of x plus 2, I leave behind a factor of 4x from the first term and a factor of minus 7 from the second term. Remember a few screens ago when I talked about special products? Well, each one of those special products leads to a special form factorization. These first two forms are called perfect square trinomials, and the last form is called the difference of squares. We also talked about formulas for the difference of cubes and the sum of cubes. Let's see a couple of examples. How about if we wanted to factor x cubed plus 64? Well, this is the sum of cubes. And our a expression is x, and our b expression is 4, because 4 cubed is 64. So according to our special pattern, x cubed plus 64 is going to factor into a plus b, that's x plus 4, times a squared, so that's x squared, minus a times b. X times 4 we generally write as 4x, plus b squared, that's 4 squared, which is 16. How about x squared plus 64? Now this looks like a special form, but it's actually not. Think about trying to factor x squared plus 64. We could imagine a linear coefficient of 0 here. And if we had a linear coefficient of 0, what we would be looking for is two integers that multiply to 1 times 64. So that's 64, and add to 0. Well, think about pairs of integers that multiply to 64. They'd either have to both be positive or both be negative. There's no way we're going to add two positive numbers and get 0, nor is there any way we're going to add two negative numbers and get 0. So it just has got to be the case that the binomial x squared plus 64 is prime. Alrighty, let's move on to quadratic equations. A quadratic equation in one variable, when that one variable is x, is an equation that can be written in the form ax squared plus bx plus c equals 0, where a, b, and c are real numbers and a does not equal 0. Some quadratic equations can be solved using the zero product principle. The zero product principle says that if a times b equals 0, then either a equals 0 or b equals 0. So for example, if we wanted to solve x squared plus 10x plus 24 equals 0, since 6 and 4 multiply to 24 and 6 and 4 add to 10, what we could do is we could begin by factoring the left side of this equation into x plus 6 times x plus 4. By our zero product principle, the only way we're going to multiply these two expressions and get 0 is if one of the two expressions equals 0. In other words, x plus 6 has got to equal 0, or x plus 4 has got to equal 0. That means x equals -6 or x equals -4. So the solutions are -6 and -4. Some quadratic equations can be solved using the square root principle. U squared equals k if and only if u equals plus or minus the square root of k. Here we're thinking of k as some non-negative number. So let's solve x minus 5 quantity squared minus 24 equals 0. I see a perfect square, so I'm going to use the square root principle. If I have x minus 5 quantity squared minus 24 equals 0, x minus 5 quantity squared equals 24, so by the square root principle, x minus 5 equals plus or minus the square root of 24, which is plus or minus the square root of 4 times 6, which is plus or minus the square root of 4 times the square root of 6, which is plus or minus 2 square root of 6. So x minus 5 equals 2 square root of 6, or x minus 5 equals -2 square root of 6, which gives me x equals 5 plus 2 square root of 6, or x equals 5 minus 2 square root of 6. So the solutions are 5 plus or minus 2 square root of 6. All quadratic equations can be solved using the quadratic formula. The solution to a quadratic equation of the form ax squared plus bx plus c equals 0 is x equals the opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2a. The radicand b squared minus 4ac in the quadratic formula is called the discriminant. Let's explore why that's important. Well, b squared minus 4ac, that's the expression underneath the radical. That's what the word radicand means. And the value of that expression tells us something important about the solution set to the quadratic equation. Specifically, if the discriminant is positive, then the equation has two real solutions, because the square root of a positive number is a positive number, and so when we add the square root, we're going to get one solution, and when we subtract the square root, we're going to get a second solution. On the other hand, if the discriminant is 0, then the equation will have exactly one real number solution, because the square root of 0 is 0, and it doesn't matter whether you add or subtract 0, the final result is the same in both cases. Finally, if the discriminant is negative, then the equation has no real number solutions, because there are not real number square roots of negative numbers. Let's solve x squared minus 5x plus 1 equals 0. In this equation, our value for a is 1, our value for b is -5, and our value for c is 1. So our solutions are x equals the opposite of b, so that's the opposite of -5, plus or minus the square root of b squared, so that's the square of -5, minus 4 times a, which is 1, times c, which is 1, all over 2 times 1. So that's 5 plus or minus the square root of 25 minus 4, all over 2. So I can see that the solutions are 5 plus or minus the square root of 21, all over 2. Then we talked about quadratic equations in two variables. A quadratic equation in two variables, y equals ax squared plus bx plus c, where a doesn't equal 0, graphs to a parabola. The x-coordinate of the vertex of the parabola is x equals the opposite of b over 2a. The vertical intercept of the parabola is the point 0c. The x-coordinates of the x-intercepts, if there are any, are the solutions to the equation ax squared plus bx plus c equals 0. And the line x equals opposite b over 2a is the axis of symmetry. Symmetry can be useful when finding additional points on the parabola. And the parabola opens upward if a is greater than 0 and opens downward if a is less than 0. That was a whole lot of information. Let's see it in the context of a graph. Here I have a graph of y equals x squared plus 2x minus 3. The x-coordinate of the vertex is opposite b over 2a. So for this parabola and this equation, that's the opposite of 2 over 2 times 1. That simplifies to x equals negative 1. So x equals negative 1 is the axis of symmetry, and since the vertex lies on the axis of symmetry, the vertex has an x-coordinate of negative 1. The y-coordinate of the vertex can be found by substituting negative 1 for x in our equation. 1 plus 2 times negative 1 minus 3 is negative 4. The y-intercept is the point 0, negative 3. The y-intercept has an x-coordinate of 0, and when I replace x with 0, I see that y is negative 3. The x-intercepts are the points negative 3, 0, and 1, 0. X-intercepts have y-coordinates of 0. If I take the equation 0 equals x squared plus 2x minus 3, and I factor the right-hand side of the equation, I can see from the zero product principle that x has got to equal either negative 3 or positive 1, since one of those two factors on the right has to evaluate to 0. We finished up Math 65 by talking about functions. We began by defining a relation. A relation is a set of ordered pairs. Then a function is a special type of relation. A function is a set of ordered pairs with the property that no two distinct points in the set have the same first coordinate. The set composed of all of the first coordinates of the ordered pairs is called the domain of the function. And the set composed of all of the second coordinates of the ordered pairs is called the range of the function. Each input from the function's domain generates exactly one output from the function's range. We call the first coordinate of the point the input, and we call the second coordinate of the point the output. And then we introduce something called function notation. We read this expression as y equals f of x, and we are going to input a value for x, and we're going to output a value for y. So let's look at this function. In this function, the domain is the set of numbers 4, 3, and 8, and the range is the set of numbers 7 and 5. 7's already in the range, so we don't need to specify that it's in the range again. Once a number's in a set, it's in the set. So let's see what happens when we input 4 for x. Well, we have the point 4, 7 in our function set. So the value of y is 7. So we say, using function notation, that f of 4 equals 7. The value of the function f when x is 4 is 7. What happens when we input 3 for x? We have the point 3, 5, so the output for y is going to be 5. F of 3 equals 5. The function value at 3 is 5. When we input 8 for x, from the point 8, 7, the output for y is 7. F of 8 equals 7. The function value at 8 is 7. I think we've milked this function for all it's worth. Let's look at another set. So here's a new set. Suppose we input 6 for x. Well, all sorts of alarms are going off. What's up with that? Well, I see that we have 2 points in our set that have a first coordinate of 6. So our function is confused because our function can only output one number, but it doesn't know should it be outputting 9 or should it be outputting 1. Well, here's the fundamental problem. This set is not a function, because a function is a set of ordered pairs with the property that no two distinct points in the set have the same first coordinate. Here's 2 points that have the same first coordinate, so this set of ordered pairs is not a function. Function notation makes no sense when you're working with a set of points that's not a function. One last example. Let's evaluate f of 2 when f of x equals x squared minus x plus 5. Well, what this formula is telling me I need to do with 2 is I need to begin by squaring 2 because f of x begins by squaring x. Then I need to subtract 2 because f of x next subtracts x. And I need to finish up by adding 5. So altogether, this is 4 minus 2 plus 5, which is 7. So the function value at 2 is 7. And that ends my review of Math 65. Remember to work the practice final in your telecourse packet before watching Lesson 20.